So hello everyone and welcome to this next lecture. So in the previous lecture, we had simulated the boost converter and analyzed its waveforms. So in this last lecture of the boost converter series, I will simulate an open loop control for the boost converter. So before I get started with this lecture, as before, a little bit of background that if you are interested in these kind of video lectures and you would like to do an online course, I do have a more comprehensive online course on simulating power electronic circuits with Python. This is on this site called Udemy, and it goes through the entire process of how you can install, how you can simulate, which includes installing the software, some basic theory, and finally a simulation example. So the link to this course is provided in the description for this video, so if you're interested, please do check it out. So back to the lecture. So now that we are done with the basic simulation, let me just go over to the file browser, and this is where we stopped off. We had stopped off in some of these simulation waveforms. Now what we had done so far was an open loop simulation. So for example, this is what we had done. We had fixed the modulation index, or rather the duty ratio. So the duty ratio, which is called modulation signal, was fixed at 0.3, right? And we had simulated the circuit. So this is basically a constant duty cycle simulation. Now in reality, you need to regulate your output voltage to a particular value. So what that means is you have a PI controller that measures the output voltage and controls the duty cycle accordingly. Now we will not go into PI controller design, as that is a bit complicated and that needs a little more time. What I will do instead is an open loop control, and for that we just have to copy some of the stuff from the buck converter example. So in the buck converter example, I had this simple open loop control file, which is a Python file. Here I had merely increased the modulation signal from 0 to 0.8, right? So I'm just going to copy this over to my boost converter example. So let me just go and copy this. So I'm just going to go here, copy it, and paste it into the boost converter folder. So now you see this file has been added. Now that I've added the file into the directory, I just have to add it into the simulation. So let me go back and go into edit control and add another file. Here I have to choose this file where I have just added it. So make sure you're in the boost converter directory and go to openloopcontrol.py. So I'm going to just call this open loop control. You can just give any name you want, that's not a problem. And here I'm going to configure the control. Now as before, to accelerate this process, I'm just going to go to the file browser rather, open this again in a new folder, go to the buck converter folder, and I'm going to copy the descriptor file. Alright, now really speaking, if I can just edit all the parameters, right? I can edit all the control parameters, but I'm using the same file, so why bother? Let's just upload the descriptor file. So I'm just going to go again, make sure in the boost converter directory and select the open loop control _ desk.csv. So the descriptor file will have the same name as the Python control file, but will have an _desc at the end of it, and it will be a CSV file. So this is a descriptor file which has the same control variables as your Python file, right? So let me open this. It is not done. It is not enough to just choose it. You must click on upload file. So now that I uploaded it, you see that all the variables have appeared, right? So there's not much in this file because all we are doing is changing the modulation signal. There's only one change that we need to make, and that is here we have given a constant modulation index or duty ratio. We have to comment that and equate it to the open loop control modulation signal. The open loop control modulation signal is set in this open loop control.py file, where I have declared open loop control modulation signal as a variable storage type. So if you come here, it's a variable storage type, which means it's a global variable. Now once you have a global variable, it's available in all control files. So by equating it to the modulation signal, this is a local variable. I am now making the modulation signal generated by this open loop control file available to the entire simulation. So I'm accessing it and I'm equating it to the modulation signal. This in turn is fed to the PWM stage. So therefore we have hooked up our open loop control to our PWM. So let me go back to the simulation and let's go to the run page. So this is the view output, and here I can now click on run. So the simulation is running. As always, when you run the simulation, please do go to the command line and check that there is no unexpected error. This is very important, particularly when you have control files, because when you have control files, there could be some silly syntax error or something else which is not possible to catch with the simulator, which shows up in the command line. So now that we have this, let's go over and plot the usual suspects. Let's plot the output voltage. And let's go to the file browser. This is the output voltage, and this is our output voltage. So you see what's happening here. This is where initially it starts at 0, it gradually increases, and it is probably increasing. So we have, let me go back to the circuit simulator, edit circuit parameters, view components, and our voltage source is 12 volts. So we have an input voltage of 12 volts, and therefore it will be interesting to see what our final output voltage will be. Let's plot it again, and you see it has stabilized. So now the output voltage, let me zoom in a little. The output voltage is around 55 volts, right? So let's go over to our spreadsheet and let's try to calculate what we expect. Our input voltage is 12 volts. Now the boost converter, the formula is, it is the input voltage divided by 1 minus the duty ratio. The final duty ratio is 0.8. So let's put 1 minus 0.8, and you have 60 volts, right? So we are expecting a voltage around 60 volts and we have around 55 volts. I guess we are losing some voltage because of losses and ohmic drops and other things. That's only expected. Now let me delete this and let's check out some of the other plots. Let me just save this before. Let me check out some of the other plots. Let's go to the simulation and let's plot the inductor current. So let's first plot it and then we'll zoom in. This is the inductor current. So as always, you see the inductor current also starts up because we are starting up with almost 0 modulation index. So therefore there is a gradual increase. If we suddenly set a high duty ratio, there's going to be a spike in the current. And the reason for that is because the capacitor is initially uncharged and the current has to be spiking through it. So now this is the inductor current. Let's zoom in at some point, let's say 0.2 to 0.201. And you see this is the inductor current, which is only as expected. When the switch is turned on, the inductor current rises. When the switch is turned off, the inductor current falls because the inductor now charges, or rather the inductor now discharges to the capacitor charging the capacitor up. So this is perfectly okay. I think we can accept this. Now at this point I would like to end this lecture as I do not want this to get too long. I would strongly suggest that if you are watching this and coding along, please do try to create all the other plots and analyze them as well. They would be fairly similar to what we did in the previous case. The only difference is now there is a transient that goes from 0 to 0.8 where the modulation signal changes from 0 to 0.8, but otherwise the results should be more or less the same. So I would encourage you to go and check it out. It would be pretty much the same. Before I do, I would like to stop the simulation and let us wind up, in the sense I'd like to export all our values. So let's go to edit circuit parameters, let's go to view components and export the parameters. So as before, we do not have a boost converter underscore params.csv. So we have only the circuit file. This is the circuit file. Now as I said before, when you're collaborating with people, it's better that you be able to send them files. So it's good if you can export. So therefore we export the parameters. Let's go back to the file browser and you see now there is an underscore params.csv. So if we open this file, you will see that these are the parameters of your circuit. Right? And if you have more circuits, you can do it for all your circuits. You get that many different underscore params.csv file. So it basically adds underscore params to whatever is the name of your circuit file, and now you have a backup of your parameters. So you can share this file with any of your collaborators. And we can do the same. Actually, we don't have to, because the open loop control file is the same. We can however change, and we don't have to change gate signal underscore dot desk either, because we didn't change either of them. So with this, we are pretty much done. I will soon make these files available for download through something else, and this is something I'll post in the next lecture. So this ends the series on boost converters. In the next series, I will start with buck boost converters. So as before, if you have any questions or comments, please do comment. Please do add your comments to this video, or email me, or connect with me on social media. With this, I will stop this lecture as before, and we'll see you in the next lecture, which will probably happen next week. So thank you so much for watching, and goodbye for now.